Thank you, and good afternoon, everyone. I'll start off with a story about my daughter's birthday party. So my daughter recently celebrated her birthday party, and out of all the games that she wanted to play with her friends, pin the tail on the donkey was the one she picked. Well, truth be told, it was a unicorn because she loves unicorn. And why I'm telling this story, because each kid in this game was asked to put on a blindfold, and then they were given a paper tail in their hand, set out on the journey of taking that and hit the destination, which was pinning that on the donkey. Now, as you can predict, no one came close, no one was able to hit the target. Well, how could they? They were wearing a blindfold. Imagine going to a job and then asked to do a job with wearing a blindfold on. And that happens. If it happens, then it's impossible for anyone and anybody in any industry to do it. But not for the engineers in the energy sector. They have to devise, they have to optimize, they have to come up with different ways to extract oil and gas under the reservoir. And they have to do it without understanding what's happening inside the subsurface. Subsurface is a very complex geological puzzle where you can't really touch and feel, but yet you have to come up with numerous probabilities of actions that you have to do for maximum extraction. So how do they do it? They do it through simulation software. And that will be the focus of my talk this afternoon. In 1997, Japan Oil Engineering, JOE, approached computer modeling group CMG, 1997. And this was right after when the Kyoto Treaty was adopted. If you guys recall, Kyoto Protocol or Treaty was fully in effect in 2005, and there were close to 192 participant countries by 2020. And the idea really was to make sure that the harmonization or the practice that United Nations climate framework put out there to combat the greenhouse gas emissions, with focus on 7 different gases: carbon dioxide, methane, nitrous oxide, to name a few. So they had approached CMG in 97 with this novel concept of carbon capture and storage to really figure out how to properly model and simulate carbon dioxide inside the ground, inside the saline aquifers. The challenge was, at that time, there was no know-how that existed. There was no physics, understanding of physics, nor the chemistry that existed at the time, something to go back to. So together with CMG, they helped build state-of-the-art simulator, which is geomechanics coupled solving equation of state, EOS. And this simulator became a simulator called GEM, which right now is the industry standard when it comes down to solving CCS, geothermal, hydrogen, etc. Became very exclusive for solving the carbon capture inside the saline aquifers. So let me talk about the problem at hand. We all are under the guidance of net zero. We heard this morning about how optimistic we are, how the right timing is in place on energy transition, and there are multiple solutions that come under this umbrella. I just spoke about carbon capture and storage. There's hydrogen, there's geothermal, wind, solar, even lithium. So there are multiple technologies or solutions out there right now which are still in the early phases of development. The challenge at hand is very early in the development, a lot of capital expenditure, infrastructure is required. So the journey ahead is quite steep in some of them. The reason I picked up CCS today is because this is something that oil and gas industry has been doing it from a carbon dioxide perspective, understanding CO2 and leveraging CO2 for enhanced oil recovery over the decades. There is also existing infrastructure to a certain extent that can be used in a way. So CCS is something that we can start the journey right now. And the right tool is important because in speaking to one of our clients who recently, a couple of years ago, they were fined close to $300 million. Why was that the case? Because there was not the right modeling and the simulation that was done. And in their words, had they invested in the right technology, the right modeling, the right physics, geochemistry, geomechanics, it would have been a fraction of the fine that they would have paid to the regulators. So let me talk about the reservoir simulation and how reservoir simulation has a direct transfer aspect to it. If you understand reservoir simulation, the model really is you take seismic data, you take the seismic data, pictures of the earth, bring that together into static modeling. From static modeling, you feed that into fluid flow modeling. Then you run various history match and proxy modeling. And then you start to forecast for economic reasons, you calculate the NPV. Now you take that and apply specifically from CCS perspective. Here you're modeling, the first step is you're modeling the storage site. That is the focus area for where CO2 will get injected. From there you run sensitivity analysis, like looking at really injection rates and long-term storage impact and the integrity of the storage site. That feeds back into different uncertainty models. Reporting comes out, goes to regulators, where you are able to get a permit done. But you're not finished in this one cycle. This cycle continues because it's a loop. The measurement, monitoring, and verification has to be there because the physical data of that site needs to get validated with the simulation model. And it's a closed loop because you're trying to not just store CO2, you're trying to ensure that the CO2 stays inside the ground for 50, 100, 200, 300 years. So hence the simulation that has been used for reservoir simulation becomes very, very critical in terms of how to do it. So the example that I gave around the fines, this slide kind of gives justice to the fact as well that since for the last 22 years, I would say, in US itself, the oil and gas operators have been fined close to $54 billion the last 22 years in terms of violating the Clean Air Act and to various regulatory bodies. The fines are actually going to get more stringent, especially as we start to become more accelerated on the energy transition route. And the time period, that 22 years, is going to become much more shorter because there's going to be much more projects coming along the way. So technology really becomes very important. JOE, Japan Oil Engineering, had a line of sight to understand why simulation is so important. So you really cannot take a lot of risk in terms of on carbon capture, because when things go wrong, you can get fined, you can get sued. There's a brand societal impact that can shut you down. In some extreme cases, loss of life can happen, caused operational impact as well. So stakes are very, very high. So not using a technology is not an option. Using a subpar technology is not an option. And this is not the place for experimentation. You really have to go with the tried and tested simulation modeling where you can mimic all the possible constraints, the behaviors of CO2, the liquids and the fluids, interaction with the rocks, because it's very volatile in terms of how CO2 is going to behave under the ground, and it stays there, super important. So simulation is going to be the key in terms of going forward. This picture kind of gives an idea of how complex things can get. There are four different ways where CO2 starts to get trapped. You have the structural trapping where CO2 stays inside the ground. The cap rock integrity really is super important, where CO2 stays inside. Solubility, where carbon dioxide starts to dissolve into water, like a carbonated water. Then you got mineral trapping. That's most safest form of having CO2 staying inside the ground, because it starts to become minerals and calcites over 50 years, 100 years, and so on. And then you have the residual trapping. What you also have to make sure is that you're ensuring the integrity, pressure, and the temperature, and the geomechanics and the geochemistry. Because when geomechanics can go wrong, you can have leakage at the walls and at the surface of the reservoir. Geochemistry, you can have all kinds of injection issues that can have issues in terms of the volume and the mobility of carbon dioxide inside the reservoir. If your injection pressure is not optimized, you can have faults starting to leak which were not there before. So a lot has to kind of model in in terms of how this all will play out from a simulation perspective. Now, I'm not here to talk a lot about the physics, and it's not definitely a physics class in any way, but I do want to give you the context of complexity and how simulation technologies have to be making sure that they follow the law of physics. So picking 3 or 4 over here, conservation of mass. We all understand that the total mass entering inside the system has to be the same total mass exiting the system. In this case, we are entering a new mass, CO2, that's going inside the ground. So the complexity for that, to manage it, especially when it's not isothermal in nature. Conservation of energy. We all remember the law of physics. Energy can't be created nor destroyed, but can be changed from one form to another or transferred between the objects. Now, why it becomes critical for CO2, again, in terms of its mobility, as it solves for the feasibility in this particular equation. Fluid phase behavior, solving the equation of state. The nature of fluids, they're very sensitive to extreme cases of temperature, pressure, and composition. CO2 especially is very volatile. So how CO2's behavior is going to change under the ground, under those various conditions, is going to be very important to be solved for physics. The last one, fluid flow, I'll pick on is, I'm sure you guys know the famous Darcy's law, which is really trying to calculate the CO2 velocity, especially taking into account the permeability and the natural pressure ingredient at the reservoir. So a lot of physics and geomechanics and geochemistry needs to be settled out. Physics isn't changing, but the behaviors of phase flow behaviors continues to change. And what you see on the right-hand side of it is that when the simulator has to run so many different scenarios. There's a high-risk scenario where there's a case of carbon dioxide really popping out of the ground and leaking from the surface, and multiple other cases where low-risk scenario is what we want to achieve. So simulation technology and the reservoir simulation technology being used for CCS starts to become extremely critical, because you're trying to solve the problem as a whole, not a disjointed problem. The wells and the reservoir and the facilities have to all come together, because it's not about storing CO2, it's not just about keeping CO2 inside the ground, but there's also a transportation layer that needs to be managed as well, whether that's pipes and how CO2 behaves in pipes. So facilities and the network model has to be as a whole. From a CMG perspective, again, a little bit of an advertisement for CMG, which is important. As I mentioned, 1997, we were given the chance to build this simulator, state-of-the-art simulator called GEM. Since then, 80 to 85% of the projects in Europe, when Europe was quite big on CCS, now a lot of focus on geothermal and hydrogen. And with US, with Inflation Reduction Act, so many projects are coming our way. There's a big project happening in Pathway Alliance in Canada, where 6 largest operators have come together to solve for carbon capture and storage. And we see a lot of that, but we don't want to stop in terms of what we have built 20 years ago. Our scientists are taking these equations and they are adding more equations to it, working with different industry partners like Kongsberg Digital in Norway, where we are starting to look at the wellbore transient model as well, because that's super important to get that into equation and really start to solve it as a comprehensive solution, fit for purpose solution. These equations right now, they're just tiny bucket of what could be, because when you take a multi-million grid cell model, you can imagine the scale and the complexity that needs to happen. So how do you evaluate risk? You mitigate that by doing modeling. For the finance guys, how are you forecasting based on the changing commodity prices? You're doing financial modeling. The CEOs looking at buying companies, mergers and acquisitions, you're doing a lot of business modeling. The regulators, will the regulators approve a project which hasn't gone through extensive risk assessment? They won't. So simulation technology is super critical. And the advantage that we have as an industry right now, simulation technology is one. We have high resolution seismic data. We have AI, ML powered seismic interpretation. We have access to engineers who are trained over the last decades, who can really now come together and see the problem as a whole. The industry still struggles from silos, and technology is the enabler in terms of solving those silos. The collaboration can happen through technology, because you really start to solve the problem as a whole. It's not just one departmental problem or one company's problem, it's a whole problem. And technology gives you that speed and the scale. And there was a talk in the morning about how speed is super critical. CCS has been talked about in the past. It's not that it hasn't been talked in the past, but now there's a momentum in place, there's a funding in place in some cases, government support is in place. So there's a lot of things that are coming together. Let's take advantage of the technology to enable that and get that scale and acceleration that we need. So back to my daughter's birthday story. So I saw all her friends going first. She was the birthday girl. She went at the last. She saw everyone kind of missing the target. I think I'll have to touch up my walls because a lot of them missed the mark completely. But when my daughter's turn came, she was smart, although she was wavering off her coordinates, but she was able to pin the tail at the right spot of the unicorn. And I was super proud of her, super smart. She was smart about doing it. The friends were very upset. And why she was able to do it? She took the blindfold off. And that's the key message that I'm portraying over here to you guys, is that there's a lot of complexity. There's a lot at stake. There's a huge cost of carbon capture, from carbon capture to sequestration for transportation. And if things go wrong, there are multiple consequences around it. But technology and battle-tested technology built over the years, combined with geomechanics, geochemistry, high-performance computing, physics, is available for us now to move forward. And all we have to do is remove the blindfold. Thanks very much.